These are your notes on molar solutions and titrations. So we remember that molarity is moles of a solute per liters of a solvent, and we can use molarity as a conversion unit within a T-chart. A new term that you need to know is this thing called equivalence or equivalence factor, and that's just the number of hydrogen ions or hydroxide ions that are donated for an acid or a base. And so 1 mole of HCl has 1 mole of hydrogen ions, 1 mole of H2SO4 has 2 moles of hydrogen ions. So it's just basically the number of hydrogen ions or hydroxide ions donated from the compound. So for HCl to have the same number of moles of hydrogen as 1 mole of H2SO4, I would need 2 moles of HCl. So then if I have 10 moles of H2SO4, how many moles of HCl would you need? You would need 20. So just very simple understanding of that comparison. And like I said, OHs are the same, so if I had 4 moles of NaOH, I would only need 2 moles of magnesium hydroxide, because that little parenthesis 2 right there, to have the same number of hydroxide ions. So molar solutions and titrations, a new mathematical equation / conversion unit that we might have is normality. So normality is the number of equivalents, remember equivalence is hydrogens or hydroxides, per liter of solution. We also can calculate normality as molarity times the equivalence factor. So we can use this top one because it is a derived unit as a conversion unit within a T-chart, but we can also use it if we know the molarity and if we know the equivalence. So just a reminder, molarity is moles per liter, and equivalence is just equivalence per liter. So this is why we can say molarity times equivalence equals normality, because it's the equivalence per liter of solution. So we can also use the normality concentration to determine the pH or the PaOH. So it's just another way to calculate that pH. Maybe if I don't have my hydronium ion or hydroxide ion concentration. So I could take the negative log of the normality concentration to also find the pH. So remember, X is equal to H or OH. So again, we can find that normality most of the time with molarity times equivalence. So to titrate, the hydrogen ions from the acid will react with the hydroxide ions from the base to form water. So we will create a neutral solution because we produce water and salt. So to reach an equivalence point in a titration, it's essentially the neutralization point between an acid and a base. So the number of hydrogen ions must equal the number of hydroxide ions. So that's what we call the equivalence point. So when we are titrating, we have that titrating in general is an experimental technique that provides a sensitive means of determining the chemically equivalent amount of acids and bases needed for that neutralization part. We are going to shoot for a 5% error or less when titrating because it is a very sensitive means of titrating or means of experimenting. We can literally go drop by drop in terms of our volume difference. So the algebraic titration equation is there, but I'm going to move on to the T-chart titration equation because that is what we will be using. And so our T-chart titration equation, so if I know more information about the base, meaning if I know the volume of the base that I'm using, and I know the molarity of the base, and I only have the volume of the acid, I'm going to be able to calculate for the unknown acid molarity. So this is basically what we're going to be doing in lab. This T-chart right here, ladies and gentlemen, should show up in your background section, please, of the big formal lab. So this should be in the monoprotic, diprotic background section, as well as the dilution background section. So please make sure that that shows up. So when you're doing this, you can also know more information about the acid, where if you had the volume of the acid and the molarity of the acid, and only the volume of the base, you could find the unknown base molarity there. So these, again, this conversion unit right here is just our base molarity. If I start with the volume of my base, remember I like to start with units that are in the single form, not derived. So if I start with the volume of the base, I can use the base molarity, and I can use the mole ratio to be able to calculate for the moles per liter of the acid, which gives us the molarity. So this is really important. Most of the time, we want to cross out the moles and put that down here to be able to cross it out. Well, we don't actually when we're solving for molarity, because the moles of whatever we're solving for must go on top to be able to give us moles per liter, or moles per volume. And so the same thing can be said for the opposite equation. So you'll use this slide a little bit as a reference, but I think that you guys will get good at understanding how these things can cross out, which is why I want you guys to do them as a T-chart, because your understanding of this stoichiometry process and where things go within the T-chart and how to cross out different units is really good. So I don't think that you're going to need this help slide for very long. So what is an equivalence point? So it's the point in the reaction when equal number of moles of acids and bases have reacted. So basically it's when we have a neutral solution, and the neutralization reaction will happen when I have 1 mole of basically each thing, acid, base, and water and salt. So we have an equivalence point, but we also have this thing called an end point. An end point is the point in the reaction where the indicator starts changing color. So we worked on what an indicator does and what an indicator is when we did our household pH lab. So just remember, indicators change color in the presence of acids or bases. So phenolphthalein is what we will use in the lab, and phenolphthalein turns pink in the presence of a base. Phenolphtalene's endpoint, so where it starts changing color, is around the pH of 8. If you notice here, the volume of added whatever acid or base, depending on which titration experiment you're doing, okay, this is a very, very steep curve. So the difference between the pH of 7 and a pH of 8 could be 1 or 2 drops. And so this will cause a slight source of error that our endpoint of phenolphthalein is at a pH of 8. But that's why we can still ask for a 5% error or less, because the difference between this and this here is 1 or 2 drops of our acid in this case. So this is depicting a strong acid, strong base titration curve where our equivalence point is 7. And so we're going to use an indicator that will be having an endpoint close to where our equivalence point is. It would not make sense to use methyl orange in this case for a strong combination, because the endpoint is not anywhere near where our equivalence point is. So you always want to be aware of what combination you're using to be able to get the correct indicator change at the correct endpoint. And that's basically what this slide is showing. So this slide is going to help you in terms of, there's some pre-lab questions on your acid-base lab that ask you about endpoints and equivalence points for different titration curve equations. And so you'll want to kind of reach back to this and look and see kind of where the color is changing. That will tell you what the endpoint is based on the pH. So your pH is over here. So refer back to this slide, that will be helpful for you. So we can look at titrations more quantitatively. Possible combinations are as follows here. And we can actually look at what's happening before, at, and after the equivalence point. And so here we know that we've got our strong combination. Here's just a weak strong combination, both weak combinations, and then a strong weak combination. So acids down here just because my pH is 0 down here. And so the endpoint of the indicators and the equivalence point of the titrations vary based on the combination that you have. And so this slide will also help you, hopefully, with your pre-lab questions in terms of what indicator to use and when, in terms of when your endpoint is going to happen. So a titration curve shows pH at various points in a titration experiment, before, at, and after the equivalence point. So we can generate this by putting a pH meter into the actual experiment, or we can calculate the pH at various points in the acid-base reaction. We will never do this part, so I'm going to speed through these slides and kind of talk very quickly about how you can do it, but we will actually just measure, you might do this in AP, but we will actually measure our concentration and our molarity at the very end after we've reached our endpoint in our titrations. So again, there's just some different things that you can consider when titrating. So it's got 4 different environments. So when you look at a net ionic equation, let me pause here for a second, any strong acid, strong base reaction, the net ionic equation is actually going to be water. And that's because at the equivalence point, all of these things are equal. And so we can say at the equivalence point, our pH will be 7, because all of these things are equal. The hydronium and hydroxide ions are going to be equal, and we know that our concentration is 7. So a strong acid, strong base titration curve will look like this, with our equivalence point right around 7. And so our neutralization reaction here, right, it might not always necessarily create a neutral solution because we might go past our equivalence point, but we will try to reach our equivalence point. So if we are looking at our math to do this, we can actually calculate the hydronium and hydroxide ion concentration. So these are the slides I'm going to speed through. So you can calculate before the reaction with the algebraic equation of the titration equation, and you can look at, mathematically, you'll know that the equivalence point will occur at 40 milliliters of potassium hydroxide if you start with 20 milliliters of a 2 molar hydrobromic acid. And so if you titrate the 1 molar potassium hydroxide, you could figure out mathematically what your volume will be at the equivalence point. Again, I'm never going to make you do this, so I'm going to go pretty fast through these. So you can calculate the pH of the solution before the equivalence point, after the equivalence point, when you're doing that math. But again, just skip past those. Those are not what I want to worry about right now. Something to note that an equivalence point of a weak acid strong base reaction will always be basic, so it will be slightly up here, and the equivalence point of a strong acid weak base will always be acidic, so slightly down here. Okay, so just something to note there. And just our summary of our titrations. Okay, this is just a strong acid, strong base summary here. Weak acid, strong base. These will be very helpful in referencing for your acid-base lab and for your studying purposes. So again, a titration summary. One thing to note is that when you have many acids or a polyprotic acid, they actually have multiple equivalence points, and so the titration curve would show equivalence points for each of the hydrogens in the acid. Okay, so now you're going to turn to this sheet and we're going to fill out some definitions really quick, and then you're going to do the rest of the front grid and the first 2 word problems. So the equation for molarity, just remember, is moles per liter. Our neutralization equation is an acid plus a base yields salt and water. And to remember, the equivalents are just the number of hydrogens or hydroxides donated from the compound. Normality, remember, is molarity times equivalence. And it's also the number of equivalents per liter. So remember, we can use this in a T-chart if necessary. So something to note, molarity and normality are going to be the same if you have a monoprotic acid, because normality is molarity times the equivalence factor. So if you have a monoprotic acid, it's 1 hydrogen, so your equivalence factor would be 1. So this chart right here, you're going to use the information given, and you're going to find the information in the blanks. And so you're going to have to work backwards to and from. There's no specific order. You can definitely fill in all the formula weights, those are the molar masses, and it's probably easiest to start and fill in the equivalence factor. And then you're going to go back and forth using the information that you have to be able to fill in this grid right here. You're also going to do problems number 1 and number 2. So that's what you're going to work on first. When you are doing pH and pOH, remember that you can calculate the pH and the pOH when you have the normality concentration. It's the negative log of the normality concentration. Okay, so there's your first set of notes on molar solutions and titrations. You need to have the grid done and numbers 1 and 2 by the next class period.